So, good morning. And let us first recall what we did last lecture towards. Okay, so we started studying central force motion or motion under a central force. That's the more precise way of saying it. So the force was just it was along the radial direction. There's a preferred point which we choose as the origin. Okay, so so and it was useful to work in spherical polar. Okay, and immediately we saw that phi was cyclic. Okay, and p phi, which turned out to be equal to Lz, was a constant of motion. Okay, but it's not just Lz, but all angular momentum L, the vector itself. Okay, and we also proved, we showed that the motion of the particle is restricted to the plane. What was the plane? The equation of the plane. Anybody remembers?
R dot L equal to C.
Okay. Okay, so this is what we did. And to simplify things, I said that we will choose. So, I mean, one important point here is that we need L not equal to 0. Okay. So, and so exercise for you is what happens. Please play with it and figure this thing out. And so then, so the thing is, when L is not equal to 0, it picks out a direction. So the angular momentum picks out a direction in space. Okay, and so what did I do? I chose, or we chose. Let's use the royal V. We chose L dot R equal to 0 to be the XY plane. That means we chose L equal to okay, and this is just or the theta equal to pi by 2 plane. Okay, so in this, so there's an exercise which you need to do, which is to check that. What is it? Yeah, that. I mean, from conservation of angular momentum, we know it will remain in the plane. So check that the full equations of motion are consistent with. Okay, if theta equal to pi by 2, what is theta dot for all the, see, what can we say about theta dot?
0.
Okay, so we should check this, okay. I mean, it will work out, I mean, because there are fancy arguments. But what I'm asking is, just a dirty argument, look at the Euler-Lagrange equation and see how that comes about. Okay, so this is an exercise. And so once we did that restriction, we just had two variables r and phi, and and we saw how to take care of, since this is cyclic. Okay, so again, this exercise to show is that the energy, which is a constant of motion, is of m r dot square plus L square upon R square minus V of R. So again, do this exercise without assuming theta equal to pi by 2. Okay, so if you remember, if you look at this, what would E be? Because it was time independent of time, it would correspond to, PR R dot plus P theta, right? This is okay up to an overall sign which I won't swear, but I think this is correct. Okay, so you need to work this out, and so you need to show that whatever comes into this minus the Lagrangian. So I don't know how to call it. This is not. Apologies, there are L is being overused. L will be in this lecture at least angular momentum, and the script L or whatever is Lagrangian. So you understand what I'm saying, right? Do not make this assumption, and so you need to come to show that whatever L square equal to L dot L equal to whatever we have done computed L. If you remember, there'll be P phi square and P theta square coming in there. So you need to do this computation. So these are simple computations, but they will make you more familiar with what's going on. Okay, so I'll pause here so that you can just ask me any questions which from last lecture, of course, which is not obvious. Okay, so this whole combination, if you look at it just as a one-dimensional problem, this is like an effective potential of R, and I call this the centrifugal barrier. So what is today's agenda? Today's agenda is to do a very, very specific case. So today, solve the Kepler problem. Okay. So question to you is, what is the Kepler problem? Yeah, somebody? I mean,
To prove Kepler's law from
yeah, yeah, exactly. So what did Kepler saw? I mean, what kind of motion was he describing?
Motion in the
GMM by
central
R
force.
square
Hmm.
force.
Okay, that's partially correct. Someone else said something. That I agree with whatever was said. Nothing wrong in that. Someone else said something. Okay, so
Central force.
okay, yeah, but that is central force, but it's a specific central force. That's what she said. It's a so it's a specific central. Okay, so but we still have to understand what we have to get to this. Okay, and the central force we will write it to be minus k upon r. Okay, but really the Kepler problem for me, I'll define it for you. A planet of mass m1 and position or whatever and location I'll make it 2. I want it m2. Let's see why. I don't care. No, why not? Why leave it as 1? Because that came first. So let's do that. Is orbiting a sun, okay, of mass m2 and located at r2. This is the problem. Okay, interacting. Okay, they interact via the gravitational force. Okay, and so which goes as follows. It says that the magnitude of the force is equal to G Newton, this Newton's constant, m1, m2 upon r12, where r12 is nothing but r1 minus r2. Okay, so this is what it is. And what is the direction of the force? It's always
Towards
attractive.
the center.
It's not towards the center. So if there are two bodies, okay, 1 and 2, so this will attract it towards that. So this would be the force felt by 1 or 2, and 2 will feel the similar force in this direction. Does that make sense? It's along the line, of course, joining them. And not. Is that clear? So this is a picture that you should have. And so this is
But the force, the denominator of the force should be mod R12 whole square.
force is square. Correct. Thank you. The potential is yeah. Thank you. Okay. So it's an attractive. So Newton was truly amazing. I mean, so this is called the Newton's law, universal law of gravitation. What's universal about it?
It applies to the celestial objects as well as to objects on Earth and in anywhere.
Everything, it applies to any two objects. Okay. So this is what we have, and so now we need to write the Lagrangian for the system. So this is the setting of the Kepler problem. So first thing is number of degrees of freedom is how much?
1, 6.
3 for Sun and 3 for planet. Okay, so the kinetic energy will be half m1 r1 dot square plus half m2 r2 dot square. And the potential energy would be minus K upon where K is G Newton M1 M2. Okay, so this is what we have in this problem, and so this does not look like a central force problem. We need to make a change of variables. Okay, so this is not yet looking like a central force problem. Okay, so now the question is, how do we do it? How can we do that? How can we make it look like, make it into one? It's a question to you guys. Some idea? Somebody would have seen this. Yeah.
If we take center of mass as origin, then it will always be along the line joining the two masses. So it will look like a central force.
No, but the thing is, yeah, you're absolutely right what you're saying, but we need to still get 6 degrees of freedom, right? So we need to, so the correct thing is we need a change of variables. Okay, that's what I'm getting at, and this is what you're also hinting implicitly. But the way you're doing it, you'll see only 3 then, right? So what we will do is we will go from R1, R2 coordinates to a new set of coordinates, which we'll call capital R and little r. Okay, so this R will be the center of mass variables. So R is defined to be M1 R1 plus M2 R2 and the variable R will be R1 minus okay. So this is so it looks very weird. Is why do so question was why did we even choose this? Okay, so answer comes in the following way. T, if you work out T in terms of these new variables, T will turn out to be okay. So it decouples. So what is happening is that there are no cross terms. Okay, so this is very key. It leads to a separation of variables, and V just becomes only a function of R. Okay, so what we will see is that the Lagrangian breaks up into L center of mass plus L central force. Completely decoupled. Okay, so what should L center of mass be?
Just the kinetic energy
Yeah,
part.
and I forgot to define what is capital M and mu. Okay, so capital M is just M1 plus M2, and mu is okay. I think mu has some word, reduced mass. I'm not very good with names.
Yes, sir. Reduced mass.
Okay, so all my life I've been poor with respect to that thing. It's like, okay, so let us look at each one of these things separately. So now what we can see is that this thing has only 3 degrees of variables, which is the R, and this has 3 degrees of freedom, and this has 3 degrees of freedom. Okay, so after we do this, what we can see is that it's as if we have a free particle of mass capital M located at where? Capital R. Okay. By the way, this is an exercise. You have to prove this. Okay. So exercise. Prove this. Prove this. And I know some of you will be complaining, why is this guy going so fast? Because I think Kepler problem you have seen, you would have guaranteed to have seen it somewhere, at least 2 times in your career before. So these are all things which you know, but it's sort of probably not, organized properly in your head. If that is an issue, that's not a problem. You've never heard of it, that is a problem. Okay. So the reason to go over this is so that you can reorganize your thoughts in your head, and if there are any confusions, please stop me, okay, and don't complain years later that this guy was always going too fast, didn't wait for me to catch up. So that happens, okay. So first thing is this is what LCM says, and this just follows from L center of mass, and for this now the second one is the LCM, L central force, is that of a particle of mass mu moving in a central potential. Is this clear? That's what is happening. Okay. I mean, if you just focused on the kinetic energy like I did here, then you would, I don't think there is any reason to prefer, R1, R2, prefer capital R and little r over R1, R2. It's really the fact that the force depends on the combination R1, 2, which suggests this change of variables, which suggests that we can work with little r. It doesn't tell you what capital R should be, and the way you fix capital R really is to say that let's choose R such that there are no cross terms of the form. So you just write. Here's how I would do it. I would say little r is given to me, so I don't need to do anything. Okay. So choose values of A and B such that kinetic energy takes this form. Okay, this is the story. If you do that, lo and behold, that would be the logic in arriving at this particular choice. There's no other choice. It says A should be M1 by M1 plus by. It's a weighted average. That's all it says. Okay, so this is so we can quickly dispose of the free particle thing. Okay, so we can easily solve the center of mass problem, or solve for the equations is what I would say. We can easily solve the equations for R. The equation is simple. It just says that R double dot is 0. So the most general thing will be R will be some constant vector T plus another. Okay. So that would just say that the center of mass is moving with uniform velocity A. Oh, bad. Let's call it UN. Let's change it to UN something. B is okay. Okay, so it's moving with some velocity. Yeah, okay. U. Okay, so let's do a couple of limits to two situations. Okay, this is, for instance, M2 is much greater than M1. So usually, planets are smaller than the sun, and so the mass of the sun will be much larger. And if you look at what R should be, okay, and you take the limit that, so what does this say? It says, or M1 by M2 is much less than 1. So you pull out M2 from either side. Okay, so and if you look at this, you will see that capital R is R2 plus terms which vanish as order M1 over M2. Okay, and M again will be little M2 plus order M1 by M2. And mu, these are all approximate. And what will mu be? It will be equal to M1. Okay. So this is typical thing. For instance, if you take, a planet like, Mercury or Earth, this is, so to leading approximation, mu is nothing but the mass of Earth and M is mass of the Sun with some small corrections. Is this point clear? And the first term says the center of mass is actually usually object, we are treating everything like a point object, but Sun has finite size, right? Every Sun has finite size. So what you will see is that to a good approximation, the center of mass is located inside the Sun. Is this clear, what I'm saying?
Yes.
Okay, good. The second limit is also interesting. So this is usually a usual planet thing. So you can go back and check, Jupiter is our biggest planet. Is this approximation good for Jupiter? That's an exercise for you. Second one is another extreme, which is also nice and fun, because whatever we said earlier is, suppose M1 equal to M2 equal to M. Nobody says that you can't have a two-body system. And then what you get is capital R is the average of, and capital M is 2M, nothing, and mu is half of the mass. Okay, and there's a name for this, the location of R of the center of mass is called, anybody know the name? Barry Center, RE or ER. ER is American spelling. Okay, it's called the Barry Center. And in this example, and is distinct. Okay, so see Wikipedia. in Wikipedia will, of course. I use American spelling, so I'm writing American spelling. Okay, so and you might say, what about are there situations where this second thing will happen, and that's not unusual. So nowadays we are seeing we are seing gravitational waves coming from two black holes merging with each other. So this is it's a similar system, and but there's no typically the two black holes will not have will have masses which are comparable. So the second situation would be sort of relevant. And okay, so
Sir, most of the star systems are binary now, so even then.
yeah, if you're taking the two suns, if you have two binary suns also, right, that's still true. But it depends on the what I'm saying is that when you think of planet and sun, you think more in terms of one. But if you take of two suns or two black holes or one neutron star, two neutron stars or one neutron star and black hole, they will all, be closer to the second situation rather than the first. That's all I'm saying. Okay? Not very deep, what I'm saying. So, I don't know, today is going slow, but that's not a problem. So now let's do some history. Okay. First thing is that Kepler studied data on this problem and the data was taken by Tycho Brahe, and with this he came up with his 3 laws of planetary motion. All of you know this. Okay, so this is the first historical thing, and so Kepler, in some sense, Kepler didn't derive anything, but he fitted the data to some simple observations. It didn't matter which planet he was looking at; all of them satisfied some, properties. Some aerial velocity is constant, and stuff like that, and so that's what happened. And then came Newton. He did several things. I mean, he proposed the universal law of gravitation. Developed calculus. To solve the equations of motion. And proved Kepler's 3 laws. I guess all of you know this, right? Okay. So this is the things which you would know. And there's a third part to the story. Einstein, okay, tried to reconcile Newton's universal law of gravitation with the theory of special relativity. This is something which we will see in this course, theory of special relativity. Okay. So this led to what is called general theory of relativity. So my friend Rajesh Kopakumar, he had a very interesting statement which he made, and he said that there is nothing special about the special theory of relativity because it's applicable for everything, and there's nothing general about the general theory of relativity because it deals with only one force, the gravitational force. So that's a wonderful, wonderful thing. So then, so once he has this particular thing, what one can do is some of the things which we have done, computations that we did, can be adapted into that setting, and so we can ask, so again, it's wrong to say that GR or general theory of relativity, will call this GR. Some people call it GTR. I don't know. I call it GR. GR equals to Newton's law of gravitation plus some control corrections. Okay, and so Einstein worked out what this correction is. So if you look at V effective of R, okay, that turns out to be G Newton M1 M2 by R So this is what we call K by R, right? Plus 1 plus there are a whole bunch of corrections, but this is the GR correction, leading. Okay, so Newton's law of gravitation. So, I mean, by the way, the steps to proving this is not straightforward, but the answer is easy to state, and so we will also assume that M1, M2 is much greater than M1 for R. You see? Okay, so what we see is that you get an effective potential which goes like 1 by R, additional term which is 1 by R cubed, not 1 by R. Okay, so this is what you get. Is the point clear what I'm saying? This is just the V effective of R, and there's a reason he did this, and Einstein showed that the anomalous precession of Mercury would be completely explained by this additional term. Okay, so that was so point here is that is that this term, let me just mark it, this term was needed to actually explain. All planets precess. That means they don't. Kepler's law says that they move in elliptic orbits, and what happens is that that's not necessarily true. They precess a bit, so the orbit, so the plane will not change, but it will remain in plane. So instead of going around and coming back, it will miss by a little bit. And how much is that little bit? So if you draw some semi-major axis and ask how does that precess, so you'll see it's doing something like this. It's moving. Okay, and so that's the precession that this thing. So usually most of the precession can be explained because there are there are other forces which act, which is like there are big planets like Jupiter and Saturn. So if you take a small planet like Mercury, it not only feels the force due to the sun, but it also feels forces due to the other planets. If you put them in, and then you will see that the closed orbits won't happen, and you will have a precession. But it's very, very small. It's measured in arc seconds per century. So you have to wait 100 years to see something measurable. So somebody actually, I think Leverrier, he sat down and computed all the effects and put them together. And there was a huge discrepancy. The discrepancy was the largest for mercury. So he could account for some of it, but not all the, how much the total angle. And that difference was exactly what Einstein showed. If you look at the actual number, it's some 50 arc seconds per century or something, which Einstein showed. The rest of it was some 400 or something. So 400 could be explained by standard other planets, mostly Jupiter and Saturn. But then the discrepancy, that's the anomalous, which could not be explained. So that's the thing. So it's wrong to say that Einstein proved Newton wrong he didn't. He extended the validity of Newton's laws. Okay. So I'll pause here for some questions before we get back to.
Sir, in the last case, the effective potential is dependent on velocity.
What velocity?
That L term is angular momentum, I think. That L square.
Yeah, it is angular momentum.
But
Yeah.
so
So that's a very nice question. You look below, there is c square. Okay. That's the speed of light. So whenever special relativity comes in, c will come further, right? So that object is dimensionless. You can check that. I don't think I made a mistake. So that object is dimensionless. So c square is some constant, which is, so roughly, the way I like to think about things is that whenever we talk about looking at problems, special relativity introduces one constant into the problem, which is called the speed of light, c. Okay. Similarly, quantum mechanics introduces one non-trivial constant, which is called the Planck's constant. Okay, so usually what you will find is that if you have some classical formula for something, classical means not quantum, you should not see h bar in that formula. Okay, similarly, if you look for some non-relativistic formula, you should not see the speed of light. So remember, we actually sat down and we worked out the relationship between the Lagrangian for a free particle in special relativity and Lagrangian for this thing. And when we expanded it, miraculously, the half mv square, there was a c square prefactor coming, and in the expansion, there was a v square upon c square. They cancelled each other, and the c disappeared. Of course, there was a constant like nc square, but we threw that away because that's not something which can observe. So this is something which is a way of thinking where you have to understand. So you can see that the c is a special relativistic effect. Okay. Yeah, and it depends on angular momentum. Yes. Okay. Any other questions? Yeah.
Sir, at the start of the lecture, you wrote something like total energy is half m r dot square plus. Isn't that L square by 2mr square plus?
Oh, yeah. I forgot it. 2m. Thank you. I was being very cavalier. Absolutely right. Thanks. You caught me then in there.
So there will be a plus VR, I suppose.
1 second, let me write this. Now it's okay?
Plus V of R.
Energy is plus, yes. Thank you. I was going to say Lagrangian, but actually this is correct. Absolutely correct. Anything else?
Sir,
Thank you.
sir, in the kinetic energy expression involving R1 dot and R2 dot, how are we getting cross terms from that?
There are no cross terms here. There is no cross terms here, but if you make the change of variables, if you go to capital R and capital little r, where capital R I said was some, I asked you to choose something like this. For arbitrary A and B, so you have to invert it also, no? You have to invert it and write R1 in terms of R2. You will see linear combinations coming. All I'm saying is that if you have something like this, X alpha R dot plus beta little r dot whole square. If you expand this, there will be 2 alpha beta r dot r, some cancellation has to happen. So what will happen is you will get some cross terms will come from expanding this fellow, some cross terms will come from this. These two will be such that they'll cancel each other.
Okay, sir.
Do the calculation like I said. Just do that. You'll see for yourself.
One more thing.
Okay, you need to invert this a bit, but that's okay. You can assume A is not 0, B is not 0. Okay, easy inversion. Okay, good.
Hello, can you hear me, sir?
Yes, I can.
So I was asking, so in any problem, if you are able to decouple the problem and write the Lagrangian separately, so can we also solve the Lagrangian separately? And then that's what we
Yeah, you can. I mean, it's like you can you can do them separately. Absolutely. So the statement is that suppose L equal to, let's say, write something like that. So let's say that L, is like Q1 to Qm. So this is first set. Okay, and then Qm plus 1 to say Qn and dots. Okay, so let's call all these guys, we will call them Q, capital Q vector, and let's call all these guys capital Q tilde vector. Okay, so m and n minus m degrees of freedom. Suppose you are able to write it like this: L1 okay, that means that all the variables in capital Q do not talk to the variables in capital Q dot. So you can solve this separately, independent of Q tilde. Right? You look at the equations of motion also. So what you will see, for instance, is dl by let's say Q1. Let's say that we look at some element from Qi. Okay, this is equal to dl by dl1 by dq, and same thing for dl by dqi dot is equal to dl1 by dq dot. So you can see L2 is just going away because L2 does not depend on the Q variables. Same thing will happen if you took derivatives. So Euler-Lagrange equation is what say d by dt of this. Okay, is that clear? So in our example, it is the capital R variables completely decoupled from the little r variables. And that is the reason to choose center of mass, not because it was said so in my textbook. Something nice happens. Okay. Okay.
Sir,
Yeah.
when we wrote Einstein thing, the Newton formula.
Oh, I have to go to the end, right? Yeah, this one.
Yeah, this one. When V goes to C, then the whole...
What V? There's no V in this formula. So now if you're saying in strong gravitational fields, this dot 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 is relevant. Okay, so this is like the first correction, if you wish. Okay, so if you're going to talk about, in fact, for black hole collisions, at some point for large parts, so there is this whole waveforms which people write, right? So there will be parts of it where the non-relativistic, they're more sophisticated than what I wrote here, but you can treat it like non-relativistic plus corrections. But once you go to very, very strong gravitation, then you have to work with the full general theory of relativity. You don't work like this. Okay, that's why you can see here I said M2 is much, much greater than M1. If you want to put some more conditions on, you want angular momentum to be much less than M1 square, this quantity should be less than 1 and stuff like that you can put in. But you will find that for, Mercury and all these examples, that is true. Okay, nice question, very nice question. Okay, so you can't do this approximate thing. You have to solve the full, those are pretty hard equations. And so a lot of computations are done numerically, and it took them about 20 years for the black holes, the LIGO people. It took, I think, till the numerical relativity people, they had issues with their coding issues, serious coding issues, in the sense that there was no stability in the answers. There were some issues, technical issues, which it took them 20 years, I think. So it's only around 2005 or something where these technical problems were sorted out. People found out the issues. And, research is hard. And so, the equations of general theory of relativity are pretty hard. Okay? So, any other questions? So, sadly, we are not going to start the Kepler problem today, but look, that's not so important. But the idea of using scales, I just want to this is a very, very beautiful idea. It's in some sense extension of the idea which I just said. In special relativity formulae you should see C appearing. In quantum mechanical formulae you should see H bar appearing. Okay, so let us look at the Kepler problem. In the Kepler problem, the constants are okay. Now I am not worrying about center of mass. I have solved that and one R. What are the constants which you see there? K. Anything else? Mu. That's all we have. Okay. But we know that L is okay. Then this L. So these are true constants, but this guy L is not a real constant in the sense that it depends on initial conditions. Okay, so this is an exercise which you have to solve by tomorrow. And we will start from there, okay? Construct quantities with dimensions of length. So you're supposed to take combinations, K power A, mu power B, L power C, such that you get length, time, and energy. Okay, please do this before tomorrow. It will take you exactly 5 minutes, probably 10 minutes to get started. Okay. So you do this, and this will be our starting point from tomorrow. And what we will see is that first thing you should observe is that without angular momentum, with just K and mu, you cannot solve this problem. So you will need some power of L, angular momentum, to come in the story. Okay. So, and you can go back in quantum mechanics, you can replace L by H bar. Okay. So for instance, you can look at the energy, and the energy of the hydrogen atom, is Rydberg. So Rydberg is some complicated formula, but it's very easy to see if you take K to be, whatever, E square upon 4 pi epsilon naught, and mu to be, the mass of the electron, and H bar, you ask for dimensions, you'll find that without any deep understanding, you will get something which is the dimensions of energy. And the answer is unique. Okay, so there's only one length scale you can come up in this problem, in the Kepler problem, one time scale and one energy scale. And it depends on L. It doesn't depend only on mu and K, it depends on L. So we need to give some additional initial condition. Okay, so I'll stop here, and you can ask me questions while I...
Sir, in this question, do we have to come to the dimensions of length, time, and energy by some combination of K, mu?
Yeah. So K power A, 2 power B, L power C should be dimensions of length, so on and so forth.
And sir, while in this lecture we changed our variables from R1, R2 to capital R, small r. And we said that it will make the problem look like a central force problem. So how exactly did it do that?
Because we found that the Lagrangian split into two independent parts, L center of mass plus L central force in the variable r, little r, that is. It happened, no? It's like I did not sit there and take arbitrary things and try to cook it up that way. came out. I mean, I wrote the change of variables because it's a well-known change of variables. And that's all. I didn't derive it.
Okay, sir.
But it happened, no? I mean, that you agree, right? I mean,
Yeah.
okay, so let me stop recording.